All right, let's talk about these two syntheses. So in the first one, we're starting with aniline, which you could, of course, have made from benzene by nitrating and then reducing, but we're just starting with it. And what we want to do is put a bromine in the ortho position. So this is a very similar problem to the one we did in class on Tuesday, except that instead of having an OCH3 group, we have an NH2 group. What we're going to want to do is block this position so that we can do the bromination reaction and have it not go to the para position, because as you know, because you're going to be doing a lab on it soon, if you brominate aniline, you will get mostly the 4 position, and aniline is so reactive that if you brominate aniline by itself, you're probably also not going to be able to stop at just one bromine. In order to block that position, though, we first have to protect the NH2 group. So the first thing we're going to do is acetylate that. With acetyl chloride and one of the kind of proton sponges. Pyridine and triethylamine are the 2 tertiary amines that are generally used to quench the HCl. And that will turn that into an amide. Which will now mean that it won't get protonated by any strong acid that we use in future reactions. This reaction here, where we're converting this amine into an amide, is actually one that you're going to be seeing in the DNA project, because many of those bases have an exocyclic amino group, and if you want to get reactions to happen at the alcohols and not at the amine, because the amine is a stronger base and a better nucleophile, you're going to actually have to protect that. So frequently, this one is adenine, and with the sugar, it's adenosine. And a common way of protecting that is to use benzoyl chloride and convert that NH2 group into the corresponding benzoate. This group here is abbreviated BZ for benzoyl. So you're basically doing exactly the same thing as we're doing here, which is converting that amine into an amide so that it doesn't undergo further reactions as a nucleophile, right? If it's not going to act as a base, it's also not going to act as a nucleophile, and then we'll take that benzoyl group off later. And it turns out that the conditions that you use for taking off your internucleotide phosphate group and for removing the thing from the solid support also remove these protecting groups. It's relatively harsh conditions, though. It's ammonia, and you heat it up for like 5 hours. So you'll see this same kind of reaction. This mechanism is obviously a nucleophilic acyl substitution. I'm not going to show the mechanism here, but it's your classic nucleophilic attack on the carbonyl, coming back to kick out the chloride, and then proton transfer, 3 steps. Right? Once we've done that, we can now react this with fuming sulfuric acid, SO3 gas, H2SO4 liquid. And we can block that 4 position reversibly, so we don't have to worry about it. And now we can do the bromination, and the presence of this electron withdrawing group, along with the decrease in the reactivity, this is a less effective activator now that it's an amide, because this lone pair is interacting with the carbonyl group as well as with the ring. Right, so it's a weaker electron donor, therefore it's activating the ring less. And then we've got this, which is also deactivating the ring a little bit. So now there's a pretty good chance that we can selectively just add one bromine and not two. So now what we need to do is reverse the first two reactions. We've got to unblock that 4 position, and then we need to deprotect. Right? So step 1 was protect the amine. Step 2 was block the para position. Step 3 was the reaction we wanted, right? That's the actual bromination. And then step 4 will be to unblock, which we do with dilute H2SO4. And the last step will be to deprotect, which we usually do with aqueous base. So it's 5 steps. It was 10 points. You probably recognized that it was going to be 5 steps because 2 points per step is pretty standard. So as soon as you saw that it was worth 10 points, you should have been thinking it's probably a 5-step reaction. The second one was also 10 points, so chances are good it's also a 5-step reaction. So in the second one, we're actually starting with benzene. That one I'm hoping went fairly well because it was almost identical to the one we did on Tuesday, except that you didn't have to put the amino group on there yourself. Second one is a little more tricky. What we're trying to do is introduce a nitrile and an isobutyl group, or a 2-methylpropyl. So this is 3-isobutyl, or 3 parentheses 2-methylpropyl benzonitrile. The only way you know how to put a nitrile in, I think, is using a Sandmeyer reaction. So if you're doing a retrosynthesis, the immediate precursor to this nitrile is probably the amino group. We're going to diazotize it and treat it with cuprous cyanide. So now we have the problem that we have 2 OP directors. In a meta-orientation. So that's a problem, right? We can't just do Friedel-Crafts alkylation on aniline to put that in there. The other problem is this is branched. And because it's branched, the Friedel-Crafts alkylation is very likely to end up with carbocation or uracil. So this is probably not going to be put on there with the Friedel-Crafts alkylation. It's probably going to be put on there with the Friedel-Crafts acylation and then reduced later. And that will also have the advantage that the acyl group, unlike the alkyl group, is a meta-director. So we could work backwards and say, well, if I had this, I would be able to nitrate in that position. This is a meta-director. I could do nitration and then reduce it to the amino group. And actually, the conditions for reducing the nitro group to the amino group will also reduce that at the same time. So I can actually do 2 steps at once. So having determined that this is probably put on by a Friedel-Crafts acylation, that has to have come from a nitration initially. Then we can work forwards and come up with a synthesis. You could put a bromine, that would work too. There's more than one different way to do this. So I'll talk about that one after. Now CH3. So we can do a Friedel-Crafts acylation. that will put this group in place. And it's now a meta-director, which means we can do a nitration and have the nitro group go in the right place. Concentrated nitric, 71%, concentrated sulfuric, 98%. So now you might say, do we have to do these in this order? And the answer is yes, you do have to do these in this order, because Friedel-Crafts reactions do not work on deactivated rings. So if you were to try to do it this way, you wouldn't actually manage that. That's a meta-director, right? That's great. Meta-director is what you want. But the Friedel-Crafts reaction is too weak an electrophile to work on a deactivated ring. And that's true for both the Friedel-Crafts acylation and alkylation. So if you ever have a ring that has both an alkyl or an acyl group and an electrode withdrawing group like a nitro group or a sulfonic acid, right, it's not going to happen. And that's why we didn't have to worry about over-acylation, the way we do with over-alkylation, because once you put one acyl group on there, the ring is now deactivated, which means putting a second acyl group on there isn't going to work properly. Right? Whereas with alkylation, you get over-alkylation because the new group that you put on there is actually activating it. So you do have to do them in this order. You could, instead of doing this, however, you could have done what Shui suggested, which you could have put the nitro group on there first, and then brominated, because the bromination reaction will go on a deactivated ring. And it would be possible to go from that structure to the product we're after as well, which I'll show in a minute. So now we've got this group. We want this to be reduced, and we need to reduce that to the amino group. So we can do that simultaneously by using the Clemmensen reduction. Convert the acyl group to the alkyl group and the nitro group to the amino group at the same time. And now we just have to do our 2 steps. Diazotization to get the diazonium salt. Followed by Sandmeyer reaction. With cuprous cyanide to generate the final product. So it's 5 steps: Friedel-Crafts acylation, nitration, a double reduction, reducing both the carbonyl group to the CH2 and the NO2 group to the NH2 using Clemmensen reduction, and then diazotization and the Sandmeyer reaction, which sometimes you show as a single step with a 1 and a 2. But I showed them separately and showed this diazonium intermediate. That diazonium intermediate is actually interesting, and we'll come back to that in a second and talk about other things you can do with that diazonium intermediate. So what about this? What if you nitrated first, recognize that you can't do a Friedel-Crafts reaction on a nitro compound, but you can brominate? Can we get from there to this product? And the answer is yes. Because anytime you have a bromo group or an iota group on the benzene ring, you can convert that into a nucleophile adding magnesium and ether. You would want to do this before you reduce the nitric group to the amino group. Because once you have reduced the nitro group to the amino group, you have acidic protons that would react with the magnesium bromide because the carbon anion is much more basic than the nitrogen anion. But with the nitro group, you don't have to worry about that. We could now react this with an aldehyde. And the Grignard reagent would act like this. Generating an O2 group. And the corresponding alcohol. This alcohol is benzylic. It can certainly be oxidized up using NNO2. And then you've got that same intermediate with a nitro group and an acyl group on there, which could be converted to the final product in exactly the same manner. Right? So there's more than one different way to approach this same problem, depending on whether you want to form that new carbon-carbon bond using an electrophilic aromatic substitution reaction, Friedel-Crafts acylation, or whether you want to do it using a nucleophilic acyl addition reaction using the Grignard reagent. Other questions on this one? So Friedel-Crafts reactions can only work on benzene or activated rings. And that's why you can stop it at 1.